I guess welcome to everybody. We'll want to make this as informal as possible. We had a very good symposium a couple of weeks ago. If you missed the talks and if you're interested in hearing some of them, that symposium website is linked from the seminar series website, and most of the talks were recorded and have been uploaded there, so you can access there. And I guess the second point is that part of the goal of the organizers for this seminar series is that with this extraordinary time that we live in, we can still have continue the discussions and continue the community that are engaged in the discussion. So in that, partly a reflection of that spirit, there's a Google Doc that's also linked from the seminar website, seminar series website, which currently contains the questions that came up during the symposium, and our intention is to just keep on updating that list, and you can, please feel free to send us your questions that you think are important for the field, or if you object to any of the statements that's currently in the summary, that would also be part of the discussion of the community. So hopefully the seminar series will serve the purpose of stimulating some discussions and engaging the community as we go through this last stretch of this time. So thanks me.
Yeah, thank you, Jamil. Thank you all for coming. So today, I guess I will chair the session. So we have two wonderful talks, and first one is Professor Congjun Wu from University of California, San Diego, and he will talk about time reversal, symmetry breaking, pairing, and iron-chalcogenide superconductors. So I'll keep an eye on the chat if you have burning questions. Yeah, that will help Congjun. So Congjun, it's all yours.
Okay, great. Thank you. Today is my great pleasure to give a talk in this seminar series. First, let me thank the organizers, in particular Chimil, for the kind invitation. Today, I would like to talk about a possible time reversal symmetry breaking pairing in the iron-chalcogenide superconductors. And this work was motivated by the experiment of the Uppers measurement in the Peter Johnson's group. And let me introduce my collaborators. And Longhui Hu was my previous postdoc. Now he's at Penn State, and he was the driving force of this theory calculations. And Menzhen, he's a student at UC San Diego. The experiment was done in the Peter Johnson's group, and we are his theory collaborators. And Hongye, he was also a student at UC San Diego, and he was a student of Yizhuang's youth group. And here are some references. This is the outline of the talk. First, I will give a quick introduction of the general relation of topological surface state and unconventional pairing symmetry. And after that, I will recap the experimental results in Peter Johnson's group, and which shows that there's a time reversal symmetry breaking and this gap opening in the surface state of the iron, selenium, and tellurium superconductors. And after that, I will provide a theory analysis and propose time reversal symmetry breaking pairing, and also the relation to the bulk magnetism. And finally, we will show that this time reversal symmetry breaking effect can still survive in the normal phase as a consequence of the phase fluctuation effect. Now let me introduce the background. The celebrated example of the unconventional superconductivity is the D-wave pairing state of the high TC cuprate. The D wave, which means that if I rotate 90 degrees, the gap function change the sign. Such a non-trivial structure can be reflected in the boundary state if you have a boundary along the 1-1 direction and follow the trajectory of the quasi-particle scattering. If you along this incident wave and the reflection wave, the gap function switch the sign. This means that this boundary has a topological kink, which is suppress the gap function. As a result, the zero energy end-drift mode will appear on this boundary, and this theory proposal was by Congjun Wu, and later on was experimentally observed by Laura Green's group. The gap function symmetry is always an important issue of unconventional superconductivity. For the field of the iron-based superconductor, this remains an open question after more than 10 years of research. And here I list a few of these possible pairing symmetries that was proposed in the literature, including this extended S-wave pairing and the competing S-wave and D-wave. Recently, there's a very interesting work by Qimiao's group. He considered the multi-orbital version of make an analogy of the helium-3b states, superposing of two different D-wave gap function symmetries such that this is fully gapped. And also, in particular, in the literature, there are a few gap function symmetries that break time reversal symmetry by superposing two different gap functions with a phase difference of pi over 2, also including a paper by myself. Recently, the iron, tellurium, and selenium superconductor has attracted a great deal of attention. Part of the reason is it has a non-trivial band structure topology in the normal state. It's because of the tellurium atom has a stronger spin orbital coupling and is bigger, such that its pure orbital band dispersion is large, and the cross has a crossing with band inversion with the d orbital band. And this results in a non-trivial band structure topology, such that they develop a single Dirac cone on the surface. And this structure has been nicely observed in experiments in the upper spectroscopy, and also spin resolved uppers also see have seen this spin texture. Actually, this normal state is not an insulator, but a metal. The Fermi surface cuts both the bulk of bulk band, have the hole and Fermi pocket, and also cuts the surface Dirac cone. And the surface Dirac cone, when the temperature below the TC, the surface Dirac cone also becomes superconducting due to the proximity effect. So this nicely realize the proposal by Fu and King as to for the realization of the two-dimensional topological superconductivity. And recently, there's have been quite a lot of work to study Majorana physics along this direction. However, the topological surface state of the iron, tellurium, selenium, superconductor mostly comes from the band structure topology in the normal state. It seems that it's not directly related to the gap function symmetries. It would be interesting if we can use this topological state to extract some useful information of the bulk pairing symmetry. And this is the question that I will address in the following of my talk. And next, I will give a brief recap of the important results in Peter Johnson's experiment. And basically, his group observed the gap opening in this Dirac point, and I will explain why it's related to the time-Russell symmetry spontaneously breaking. So this is the laser upper spectroscopy of the surface state. This is the normal state and goes to below the transition temperature. So basically, his group observed two different gaps opening in the surface state. The first gap is not surprising, and is just the surface superconductivity due to the proximity effect. And they also observed the gap opening at the Dirac point, also around the same transition temperature as the superconductivity. And this is not the superconducting gap, because the Dirac cone is actually below the Fermi surface about 8 milli-electron volt. And we can later we'll also say that if the gap function doesn't break time symmetry, it will not leave this chroma degeneracy either. And these two different gaps actually has a very close relationship, and this is like a data collapse. If you plot the two different gaps, the Dirac gaps and the superconductivity gaps on the same scale, and they develop, roughly speaking, at the same temperature, and their scaling also, roughly speaking, follow on the same curve. And if we look at carefully at the gap opening at the gamma point, we can, because the gamma point is quite special, this time reversal pattern, it is itself. If the time reversal symmetry would be preserved, then neither the parity breaking nor the layer ordering could leave this chroma degeneracy. And the only way to leave this degeneracy is to break time reversal symmetry. See, if you, since we don't have magnetic field, applied magnetic field, the component of Weiss field or magnetization could do the work. But a magnetization in the XY plane cannot. If the magnetization is in the XY plane, it can only shift the Dirac point in the XY plane. So the questions are, what's the origin of this Weiss field or the molecular field? And second, that can it provide certain constraints to the possible pairing symmetry in the bulk? And next, we will provide some theory analysis on the possible constraints to the gap function asymmetries. And before I move on, let me introduce a general mechanism towards time reversal symmetry breaking pairing. If you have competing gap function symmetries, and generally speaking, they cannot couple at the quadratic level because there are different symmetries, but they often do couple at the quartic level. For example, this lambda prime term, we can convert two core pairs to another two core pairs with different symmetries. And if this lambda prime is positive, by minimizing the free energy and the relative phase should be pinned at pi/2. And this means that spontaneous time reversal symmetry breaking, and this is an older result in Sigrid's review paper. As an application, we applied to a mixing singlet and triplet pairing. And in this case, they also break time reversal symmetry develop a 90-degree phase difference. And actually in the weak coupling theory, and this energetically is favorable because that is a unitary pairing. And in the BCS mean field theory, the free energy favors a unitary pairing. And please forgive me for a little digression. If this S plus I, this P plus I S type gap function actually provide a nice realization of Majorana fermions without introducing spin orbital coupling. For solid state system, the fermions electrons are often doubly degenerate. From a doubly degenerate Fermi surface to a single branching Majorana modes, actually, we need to reduce the degree of freedom by 1/4. And this P plus ice type superconductor is a surface that develops spontaneous magnetization, which means that this degree of freedom is reduced by half. Then if you have two different domains, P minus S and P plus S, then on the surface, the domain boundary will further reduce the degree of freedom by half. And then the Majorana can run along this boundary. And this is in contrast to the ordinary method that you need to begin with a normal state, a single Fermi surface, which is often unit spin orbital coupling. And this is a purely a property by superconductivity. Now let's come back to this iron-based superconductor. In order to check its possible pairing symmetry, we first need to look at this crystalline symmetry. And the each iron atom, the point symmetry group is D2D, and it is a axis of the fourfold rotary reflection axis. And the selenium atom is the center of the C4 V-point group as a fourfold rotation axis. And the inversion center lies on the bond center of the iron-iron bond. So overall, the symmetry actually is non-symmetric. Now we need to couple this magnetization with the gap functions. Since the magnetization is time reversely odd, the lowest order coupling can be written like this. And the magnetization along the z-axis is a symmetry using the group theory language is A to G. Then the gap functions, the product of the gap function to gap function symmetries should contain this A to G. And then we check that the group representations that all the possible gap function symmetries are allowed are here. And these A's, B's, actually, there are rigorous group theory symbols, but they might not be intuitive for many people in the audience. So loosely speaking, this A's means S wave-like, B means D wave-like, E means P wave-like, is a rotation with respect to the C-axis. This G and U refers to the parity, even and odd. 1 and 2 actually refers to this even and odd for the twofold rotation, and the rotation axis lies in the XY plane. And then to be more concrete, so we consider, enumerate almost all the possible gap function symmetries by considering you have one unit cell, we have a pair of iron atom, A and B, and keeping these three electron orbitals. So the gap function symmetries actually has three different parts. One is the angular form factor, then the matrix structure in the AB sublattice, then another is the matrix structure in the orbital channel. So so the actual symmetry looks quite different from the seeming symmetry of the angular form factor. The actual symmetry is a product of the symmetries of the three different channels. And then in order to couple this magnetism in this magnetization spin channel and in the orbital channel, we still need a spin orbital coupling. Then we can calculate microscopically this coupling constant through these Green's functions. If you add this spin orbital coupling in the T2G channel, and Lunhui he calculated for some representative gap function symmetries in these channels, and that you can get non-zero coupling between among this magnetization and time reversal symmetry breaking gap functions. And then let me address that this kind of time reversal symmetry breaking effect can also exist in a normal state as a result of phase fluctuation. You know, for this strongly correlated system, the superconducting system, they often have a fixed fluctuation region above the TC. which means that the gap function magnitude is fixed by the phase is fluctuating. We can model this using this XY model and J1, J2 as this superfluid stiffness. And then if they are not coupled, they will introduce, generate a crystallis Thouless temperature scales. But now, due to this quadratic Josephson coupling, we add this lambda term. And this coupling will introduce another temperature scale, which is we call the phase locking. And depending on the coupling, which is a positive or negative, if it's a positive, the phase locking will, the phase angle will be 90 degrees, the Briggs time reversal symmetry. Otherwise, the phase locking will be 0 or pi. Actually, it often leads to nematic superconductivity. But now we just consider the time reversal symmetry breaking case. And without loss of generality, we can, using the renormalization group argument, we set the J1 to be 1 let J2 smaller than J1. And then the actual phase diagram, phase structure is determined by the T star, which is the phase locking temperature scale, and also the T1, which is the KT temperature scale. So if these two channels, the superfluid density difference is pretty large, and then if we start from the high temperature in the phase 1, which means normal, there's no superfluidity in both channels. If we cool the temperature, we first have a superfluid transition, which means that you have a superfluid in the first channel, but the two channels are decoupled. And then you further lower the temperature, the phase become locked, you have a second superfluid transition. But if these two channels are nearly degenerate, and then this T star, you can see that it's significantly higher than the superfluid temperature scale. So if you lower the temperature, we will first break the Ising symmetry. Here is a time reversal to get a normal state. So the physical idea is that in this region, we have phase fluctuation in both channels, but their relative phase is pinned. So they fluctuate as together. And then as you further lower the temperature below the T1, and then they undergo the superfluid transition, enter this phase locked superfluidity. And we also Hongye did the numerical simulation for the classical XY, the coupled XY model. And we particularly look at this, the phase locking phase transition with Briggs' Ising type symmetry, and it fit nicely with the critical exponent of the two-dimensional classical Ising model. And then this result might be useful to explain at the beginning is a puzzle to us. Actually, in Peter Johnson's experiment, he already see a small gap at the Dirac point, which is about 3 milli-electron volts at TC. So this could be understood as a phase fluctuation effect. We should also have a normal state, which also break time reversal symmetry. Another important issue is that so far I have introduced an intrinsic scenario I would call is due to the complex gap functions to break time reversal symmetry. But there's another possibility that the surface, the iron impurities develop a ferromagnetism, which would also work. But this extrinsic mechanism, which is hard to explain why these two gaps, and the superconductivity gap and the Dirac gap are so closely correlated. So one possibility is that probably both scenarios works. And I think that the intrinsic scenario, the complex gap function is a driving force, but it can be amplified by the iron impurities. And this is the summary of this talk. So, we propose a possible time reversal symmetry breaking pairing in the iron-chalcogenide superconductor, and the result is motivated by this upper measurement, which is saw this gap opening at Dirac point, which means that time reversal symmetry, and it also gives certain constraints to these possible gap functions in the bulk. And thank you very much for your attention.
Thank you very much, Chongqun, for this very interesting talk.
Oh, sorry, I maybe I spent too much time.
That's okay. So I guess we can maybe spend a couple of minutes for some questions. So Daniel?
Yeah, thanks for your talk. Just one quick question. You said that your Dirac gap is observed to exist at the superconducting TC. It's finite already. Do you know what temperature that Dirac gap vanishes at?
I don't know. I think that I asked Peter, and I guess it's very difficult to tell because it's kind of experimental issue. You always have some background. It's not easy to see that when the gap exactly opens. If you move significantly below TC, you can see. Let me go to example. If you look at the data here, there's always something blurred in the middle. So it's not so easy to see that the exact temperature when the gap opens. But I'm not the experimentalist. I'm not. You could ask Peter for how he thinks about this problem.
Okay, thank you.
May I ask a follow-up question, Chongqun? So
Sure.
do I understand correctly that a T star is where both the superconducting gap and the Dirac gap open? And
You mean here?
yeah, right.
Oh, this is like a phase locking temperature. It's a temperature scale. You have two gaps. They have each channel has its phase. You can define a relative phase. You could have a phase fluctuating, but the relative phase is locked. And if these two channels are superfluid, the stiffness are reasonably close. Actually, the phase locking temperature scale is higher than the superfluid temperature scale.
I see. Okay, I see two more hands up. So Lu Li first. Lu.
Hey, Tony, nice talk. This is Lu.
Right, thank you.
Right.
Hi, Lu. Nice to see you.
So yeah, a quick question and a comment. The
Yeah.
quick question is the experiments you refer to, it's Congjun Wu sample?
Yeah, I think so. Yeah. They
Okay,
are
all right,
the
okay,
same
yeah.
place.
Right. The comment I have is in Gengda sample, when we try to measure the nonce effect, we observe a spontaneous nonce effect right below TC.
Low TC.
Below TC, right below TC.
I see.
Above TC, it's really hard to tell, but below TC, there's really pronounced spontaneous nonce signal. That suggests a time reversal symmetry breaking.
Oh, that's
And we
nice.
also test iron-chalcogenide without, so different from Gengda sample, another compound,
I see.
and such phenomena does not exist.
Okay.
So at least to us, seems that only in iron-chalcogenide we observe a spontaneous nonce effect in the superconducting state. Yeah, so that's our observation.
Actually, I read is a paper also published in PRB like last year. Is that paper?
Yeah, I assume that's our paper. Yeah.
Oh yeah. Okay, I remember you mentioned you also saw some signature in the normal state. Is that right?
I don't recall any clear signature in the normal state. At least we are not able to resolve. There might be, but we are using the difference between the thermal power versus temperature and the zero field nonce signal versus temperature to subtract the background away. It's rather hard for us to determine any normal state contribution for these zero field components. Of course, the normal nonce signal has a large superconducting fluctuation regime, like what you are suggesting here. It's just hard for us to determine whether or not there's a time reversal symmetry breaking in this fluctuation regime. Anyway, yeah, just my comment. Yeah, but really interesting story here.
Thank you.
So I see three more hands. Maybe you can just keep it these three. So Qimiao, Pengcheng, and TC. So Qimiao.
Yeah, thanks. Yeah, nice talk, Congjun.
Nice
I had a quick question. I guess we'll be hearing more in next talk about gamma to Z and all that. But I just wonder, in the experiment, Peter's experiment that you mentioned, is it focused at gamma point specifically, or is it also looking along gamma to Z?
I think it's the surface. They check both the bulk and also the surface. They use the different light polarization, the S and P. For the surface state, this is surface state. If you look at two-dimensional momentum is at the gamma point. Sorry, do you mean the Z is the electron pocket or in the
I guess I mean, presumably the bulk states also come into play in some way.
So Z is
I guess my question is,
axis.
in a bulk, I can go from gamma kz equal to 0 to z kz equal to, I guess, pi, right?
The bulk state, sorry, I didn't check the bulk state dispersion in the paper. I don't recall it has kz information, but I only remember it has the laser uppers, the light momentum is rather small. Actually, it cannot fully exploit actually it didn't say for me surface crossing. But for the
superconducting gap, the gap near EF, is that supposed to be the superconductivity on the surface, or is that superconductivity in a bulk? That is being
for this picture, is a superconductivity on surface, but in their paper, they do have the opposite result for the bulk superconducting gap.
Okay, all right, thank you.
Thank you.
Yeah, so I was curious, Congjun. I mean, so if you see this time reversal symmetry breaking, that means that you have some sort of ferromagnetic component. According to Lu just said, I mean, doesn't this mean that since he couldn't see it in iron-selenide, doesn't this mean the small possibilities induced by the iron impurities?
Yeah, that's a possibility. But the question is that this so closely. These two gaps, if you divided by their maximum value, they almost fall on the same curve. So if it's due to the iron impurity, you would expect the time reversal symmetry breaking would completely come from a different temperature scale. So
does he have a doping dependence? I mean, go to the overdope side to see, because in the iron-selenide, pure iron-selenide, there's no such effect, right?
I do know some experimental result, but I think that they are unpublished. Let's wait and see. And
okay. Yeah. Okay.
So
thank you.
Other group, yeah.
Thank you.
TC.
Yeah. Hi, this is TC. So just to clarify something. So in your model, so are you proposing that in this case, you don't need any iron impurity, but instead the pairing symmetry itself can generate some kind of effective exchange field MC, right?
Yes, but as a compromise, I would say the real life is something in between. We have both, but the driving force I would think is from complex gap function. Its effect might be small, but if you have the iron impurities, you have an electric magnet, right? The coil's magnetic field is weak, but you have the iron, the soft iron, which can enhance this overall effect. So I felt that after all, what they saw is this pretty big gap, like quite a few milli-electron volts. That might be due to the amplification effect by iron impurities.
I see. Yes, because I'm just wondering, does your model imply there's a critical MZ such that the by-1 mole can be trapped in a vortex core, but like this MZ is intrinsically arised due to the pairing symmetry, but not due to some.
They didn't apply magnetic field, so it's different from the vortex experiment. The uppers you cannot add magnetic field.
Okay, right. Okay.
Yeah, so this is not it's different from the STM type experiments.
Okay, thank you.
Thank you.
Great. So let's thank Congjun again for this great discussion and talk. We have a second talk. So I forgot to mention in the beginning. So we are, so for the workshop, we're trying to organize each day with 2 talks on similar complementary topics. So for the second talk, we have